Welcome back. In the previous video, we have completed the discussion over DC circuits. From this video onwards, we will discuss about AC circuits. Before discussing about AC circuits, we will learn something about complex numbers and how the representation of complex number will look like. Because in this whole discussion of AC circuits, we'll deal with like imaginary power, imaginary circuits, imaginary current, imaginary voltage, and all those things will come into picture from this video onwards. So we will try to look at how to represent an imaginary number in a planar coordinate system. Just consider z equal to x plus jy be the number which consists of x as real part and y as imaginary part. That's what I written over here. That is a complex number representing the vector, and x is the real part of the active component, and y is the imaginary part of the reactive component. And j is represented as under root of I mean under root of minus one. Under root of minus one is represented as j, and j square is under root of minus one whole square, that equal to minus one. J cube is equal to under root of minus one cube equal to minus j. J power 4 is 1. We know all these things, I guess. Like, and I have represented their rotation wise, uh, vector rotation wise, their angles also. Just have a look at all those things. Just how we are going to represent these complex numbers in a Cartesian coordinate system. That's the thing. In a rectangular form, a complex number can be represented as a point on a two-dimensional plane called as complex or S-plane. We are going to represent this complex number on a complex plane or S-plane. For example, z equal to 6 plus 4j represents a single point whose coordinate represent on a horizontal real axis. We are considering this horizontal axis as real axis, and this y-axis is this y-axis as imaginary axis. Imaginary axis, vertical imaginary axis. Just like we have positive, 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 I mean, negative, positive, negative, negative, positive, negative. The same thing is a first quadrant in which all are positive. I mean, horizontal axis is positive and vertical axis is also positive. In second quadrant, horizontal axis is negative and vertical axis is positive. And in third quadrant, both horizontal and vertical axis are negative. In fourth quadrant, uh, horizontal axis is positive and vertical axis is negative. Same analogy will be applicable for like imaginary axis also. These are the analogies that we read in rectangular coordinate system, right? Plus plus, minus minus. Same thing will be applicable for this imaginary points representation also. Like if we have 6 plus j4 in positive real axis, we are going to take 0.6, and in imaginary uh, vertical axis, we are going to take 4, and we are going to meet up those points, and we will form a point where we will get z equal to 6 plus j4, and we are going to connect it by using an what we call position vector in rectangular coordinate system. It's uh, some other line, just consider another line to represent it the position. That's it. This is a whole brief introduction about how to represent a complex number and what are the components in a complex number. That's it, right? Now we will dive into this what we call AC circuits. In AC circuits, we are going to have this resistance term L and C, where L is C. Thus far, we have seen the three basic passive components: resistance, inductance, and capacitance C. Here, L in a sense inductance, C in a sense capacitance. Just like we found here in this circuit, it's a basic circuit, and we have only one R, one L, and one C. If consider a scenario where we have lot of L's and lot of C's, then how to find this L equivalent and C equivalent? Just like we have find it using R equivalent by using Ohm's law and Kirchhoff's law, all those stuff. We are going to find L equivalent and C equivalent by using some other analogies. Like if inductance are in parallel, then L equivalent equal to 1 by L1 plus 1 by L2, 1 by L2, summation of I equal to 1 to n. I can write summation of I equal to 1 to n 1 by Li. And if the inductance are in series, then L equivalent equal to Li, summation of Li, I equal to 1 to n. Just like how we are going to find what we call R effective, R equivalent, just in the same way we are going to find L effective. But when it comes to uh, capacitance, see if capacitors are in parallel, if C's are in parallel, then C equivalent equal to summation of I is equal to 1 to n Ci. And if they are in like series, C equivalent equal to summation of I equal to 1 to n 1 by Ci. This is the scenario. Just try to have this basic idea how we are going to sort out all the R's, all the L's, and all the C's in a circuit. Then we will carry out all the calculations that we need. Uh, as far as in the previous discussions, we didn't have any these what we call sinusoidal curve because the potential which is living and the current which is living and everything is an absolute value and it's an like what we call it's a real value. But here in what we call uh, alternating current, we have two things. One is real part plus imaginary part. Imaginary part. Whatever the physical things that we are observing through our eyes are are the effects of these real parts. And this imaginary part doesn't cause any effect to our original system. We are taking it because to represent the another side of the curve also. That's why. That's it. We are considering this imaginary part. Other than that, it's of no use. Just I'm going to consider the scenarios where we are going to have only pure R, pure L, and pure C. Just see, in a pure ohmic resistance, the voltage wave are in phase with the current. Like whatever the voltage living here will be the same voltage passing through this resistance also. If it's a pure resistor circuit. In pure inductance, the voltage leads the current by 90 degrees. In the sense, if we are only having this inductance circuit, then current is going to lead the voltage by 90 degrees. In a sense, it's a circuit. Just consider if my original curve starts over here, it's let's consider it's V, then it's pi by 2, pi, 3 pi by 2, 2 pi. Because it's as it's a sine curve, I'm taking it as a sine curve. Now my current curve will be like this. Like this. It's going to be starting somewhere from here. This is pi by 2. In the sense, I am starting pi by 2 before the voltage starts itself. This leading in the sense, starting before it gives that sense. Giving us the expression of IELI. In pure capacitance, the voltage waveform lags the current by 90 degrees. In the sense, now voltage will start first. Now I will clean up all this mess. As from our theory thing, I have noted some important points over here. You see, the instantaneous voltage across the pure resistance we are in phase with current. If it's pure resistance, then voltage and current will be in phase. The instantaneous voltage across a pure inductor, if the whole circuit is of pure inductors, VL will lead the current by 90 degrees. That in the sense, VL will start pi by 2 ahead before of current. If it's current, then it's voltage. The instantaneous voltage across a pure capacitance VC lags the current by 90 degrees. In the sense, as we have a normal sine curve for our I, we will draw same thing for every curve. The thing which is going to change is voltage thing. Voltage. This is pi by 2. That means current is starting first. I mean, not starting first. It's starting from as usual point. But when we are considering this voltage, voltage is lagging behind the current. That's what it means. See, this is a pictorial representation of everything. We are in phase. This is the current living. This is the current living from the source. Normal sine curve. We are in phase. In the sense, same how the current is varying, then in the same manner the VR has to vary. In pure inductance, the VL has to lead, right? So it's going to start from here, where our current value is 0, but VL will be something more, just like this. I'm drawing it in rough way, but it's not the right thing. There will be pi by 2, something it might have started from here. This is pi by 2. It's leading, voltage is leading current by pi by 2. And here, just see, this is where our current starts, right? Something like that. But here it's starting from beneath of the thing where my current starts. So it's lagging behind the current. These are the basics of an how AC circuits will look like when it's pure inductance, pure capacitance, pure what we call s- resistance. These are the variations we can observe. And I'm plotting some of the graphs between V and I. See, if it's purely resistance, then VR and I will be in phase, will be in same direction, right? If I if it's purely inductance, then VL will lead, and in the sense it has to be 90 degrees more than the IL. If it sees the direction of I, then the V has to be in this direction, right? If it's an purely capacitance, then if it is the I direction, then it has to be 90 degrees lagging behind the current, right? So we are going back. It's our original direction. So I'm going back by 90 degrees over here. And this is VC. And these are the instantaneous voltage of series RLC circuit. How we are going to find is same thing. By applying KVL. Vs minus VR minus VC, VL minus VC equal to 0. By applying KVL will be applied for any type of circuit, whether it might be an AC circuit, whether it might be an DC circuit. We are going to apply. That's it. Simply apply KVL. Vs is the source voltage. VR is the voltage across the resistance. By according to Ohm's law, uh, voltage across resistance can be written as IR. And voltage across inductance can be written as L into di by dt. And voltage across capacitance can be written as Q by C. Just remember these formulas. These are the variations of instantaneous voltages and instantaneous currents in an RLC circuit. These are the basics how current and voltage varies in an RLC circuit. I hope you guys got an basic idea about how current and voltage varies in a single phase RLC circuit. We will continue our discussion in next video. Thank you guys. Bye.